All right. Let's see. We're going to go ahead and get started. I don't see that there's that many people in here, but that's okay, because it'll get recorded, and those of you who miss the live lecture will be able to replay it at your leisure, hopefully sometime this weekend. So today we're going to be talking about 1.8 and 1.9. 1.8 is strictly about linear transformations. 1.9 we'll be talking about matrix transformations and sort of trying to sort out the difference between linear transformations versus matrix transformations. And we'll come to see that matrix transformations are all linear transformations, but not all linear transformations are matrix transformations. So linear transformation. We've been talking about this, sort of everything that we've done up to this point has been computational prerequisite to actually talking about some conceptual type things. So today we're going to start looking at this particular equation, some matrix A times matrix X equals B, as a transformation, right? The matrix A is the function acting on the vector X in some domain Rn and transforming it into a vector B in Rm, right? I have an example here we're going to look at in a second, but let's look at this real quick. So think back to Algebra 1 when you talked about your function machines. Well, we have transformation machines here, right? T of X is the transformation function represented by the multiplication of matrix A times some input, right? Input X, it spits out B, right? A is coming from R sub or Rn, and B is in Rm, right? T is a mapping from Rn to Rm. Rn is the domain, Rm is the codomain, okay? We're talking about all of Rm is the codomain. That does not necessarily mean that everything in Rm is mapped to, right? We'll talk about what it means to map to all of the codomain when we talk about functions that are one-to-one and one-to. Okay. More formally, we write the transformation this way. The transformation T is a mapping from Rn to Rm. So here's an example. Let's let matrix A be this matrix, and then we have two vectors, u and v. All right. So if we say that the transformation T of X equals the multiplication of A times the input, then T of u is just the computation matrix A times matrix u, right? So I get -8, -12, -4, all right? So what you can see here is that matrix A, or the transformation T, is taking some vector in R2 and mapping it to a vector in R3. Okay? Notice that where I'm coming from is represented by the columns of matrix A, and where I'm going to is represented by the entries in row A, or the rows in matrix A. All right, so where does TV go, right? TV is going to be the matrix A times V, and where does it go? You haven't already tried to compute this. 2 times 2 is 4, plus -4, 0. 2 times 3 is 6, times -6 or plus -6 is 0. 2 times 1, 2, plus -2, 0. So the vector in R2 to 1 over the mapping T takes me to the 0 vector in R3. Okay, so that's sort of the base the groundwork of what we're going to be talking about today. This is going to be a little tricky since I'm going to be having to write a lot of stuff on the board instead of just writing on top of my slides. So let you take one last glance at this. Okay. Real quick, while I have this up here, I go ahead and mention that we call this the image in R sub n, in this case R sub R2, and this is my, excuse me, this would be my image, and this would be my pre-image, right? So where I started and where I'm going. All right, let's get rid of this. Okay. In your textbook is a more formal definition of matrix transformations, but I feel like we got the gist. So let's look at a few more examples here. Okay, my goal here is to find a vector x that maps to B. Okay, so we're looking for the x that will take me to B. In other words, we just want to solve the augmented matrix right? Okay, so we just wanted to solve this augmented matrix. Boom. So we know x is -5, -3, 1, or yes, that's fine. Which is nice. It's unique. So that means that there's only one vector in R3 that under the specific transformation A will take me to B. That's useful. That's nice. All right, we're going to do another example that's asking the same question, okay, but we're going to use some different values here. So remember, in this solution, we got a unique value of x. I bet you can guess where I'm headed with this next example. So what is the value of x under the matrix transformation AX that will give me B? So again, this boils down to simply solving the augmented matrix right? And we get 1, 0, 3, 7, 0, 1, 1, 3, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so 3 variables, right? But only 2 pivots. So we have a free variable. Right. So we'll write my solution in terms of the free variable. And then my constants. Okay. So the solution here would be consistent, however, not unique. So multiple values of x, multiple vectors in R3 under this transformation will map to B. Right? Now, when we get to it, when we start talking about onto and one-to-one, remember that this still could represent a function, right? The transformation T from R3 to R4 can still represent a function where T is a, or T of x is a x. Because it's okay if 2 things in the domain go to the same place in the codomain or in the range, right? You think about x squared in the a rectilinear as a rectilinear function. Okay. So let's look at another example here. I'm going to start labeling these examples so that if you have a question later, you can go back and talk about it. Okay. Okay, the question here is, is B in the range of the linear transformation? So is B in the range of the linear transformation that takes x to ax? And obviously, y. So what we want to know is there some x that will give me b? So it's sort of the same question, but asked in a different way. So we're just going to solve again. And we'll have 1, 3, 9, 2, negative 1, 0. So I guess we're not going to reduce. We're not looking for an exact. We're just looking for whether it exists. So the reason we didn't go reduced row echelon form, we just went row echelon form, was because the question wasn't asking specifically for the value of x that takes me to b. It was asking whether there was an x that takes me to b. And that question boils down to, can this be solved? And if it can, is it unique or not? Well, it doesn't have to be unique, I guess, but we do have to be able to get a solution. In this case, we have a problem in that last row. So you have an inconsistent matrix, so we have no solution. So to answer the question, no, this is not in the range of A because there is no value, there is no vector x that will take me to B. Hold on 1 second. That is very dangerous for you to get. You cannot be up there. Okay. So let's look at an example that may lead to an application. So far in this class, we really haven't seen that many applications, but that's like I said, up to this point, we've really just concerned ourselves with the elementary computation behind linear matrix algebra. So where might this be used? Let's let matrix A equal 0.5, 0, 0, 0, 0.5, 0, 0, 0, 0.5. Okay. We will define T from R3 to R3 to be the mapping, or excuse me, we'll define the mapping from R3, T from R3 to R3 to be the linear transformation T of x, which is multiplication of A by x, okay? And we want to find A of U, oops, T of U and T of V. Well, T of U, right, have half of 1 plus 0 plus 0. 0 plus half of 0 plus 0. 0 plus 0 plus half of -4. Okay. And TV, in general, what this matrix does is it halves my inputs. Oops. Okay. So in computer graphics, we might use linear transformations or matrix transformations to manipulate vectors on a screen, or you know, and possibly animation. If I wanted to have this quickly, I could use, I could define, or if I wanted to define a function that would have any vector I put in it, this would be a way to do that. So for instance, I could take, there's a good example in the notes, but it's a lot of drawing, so we're going to get a window that was half the size. So we call this a either contraction or dilation. It's a contraction when these values are less than 1, and a dilation, a contraction when these values are less than 1, and a dilation when these values are greater than 1. One more time. Contraction when these values are less than 1, dilation when these values are greater than 1. So dilation getting bigger, contraction getting smaller. What if those values were negative? Well, it would not only either contract or dilate, but it would flip it, right? So you can see some applications starting to come up now. Let's look at another example. Let me take a quick break and look at my email, see if there's anybody who's been trying to email me. No. We're good. All right. Okay, describe geometrically what T does to vector U and V. So we're going to look at an example here, another sort of hint at an application. So this time I'm just going to define a transformation as matrix multiplication. Okay. Give me a vector U and a vector V. And we'll see what this does. So what does T of U look like? Well, T of U is going to give me 2, 5, and T of V is going to give me 4, -2. So the specific matrix 0, 1, 1, 0 flips my variables. Right? So we call this a reflection. What line do you think this reflection is occurring over? Well, look, we're letting the first entry equal whatever x2 was, and the second entry equal whatever x1 was. So it's the line x1 equals x2. Or if you want to think back to a coordinate plane, where if this is my x1 and this is my x2, we're reflecting over the diagonal line. We're taking 5, 2, and flipping it to 2, 5. Mm-hmm. Okay. All right. Let's see. Another useful transformation. Okay, how is this transformation going to affect my inputs? Well, x is going to stay the same. Well, the x sub 1 is going to stay the same, but then I'm going to add to it twice x sub 2. So I get 9, and then the second entry is going to stay the same. Right. So in this case, I've taken 5, 2, and I'm now at 9, 2. So if you can imagine like a vector space, right? Under this sort of transformation here, I would be tilting everything over, right, but keeping the height the same. Right, so that would be my new space. Right. So from here to there, and this is called a shear transformation. Okay, we're shearing everything to one side or the other. Right. Obviously, I could maybe I don't want to shear in the x1 direction. Maybe I want to shear in the x2 direction. That's fine. I would have a 0 here and some other value here. Right, and in that case, I would be shearing either this way or this way, depending on whether the value is positive or negative. Okay. There is a huge list of linear transformations. Let's see. See page 76, and there is a large list of linear transformations, including the dilation, the contraction, shear, and a few various reflection transformations. All right. Okay, so a linear transformation is a matrix transformation where addition and scalar multiplication is preserved. So let's see. So we've been talking about matrix transformations, and here's the green stuff to erase. Maybe don't use green anymore. Talking about matrix transformations, what is a linear transformation? Let's use the shorthand. Right. So those of you who are in my BC class know the upside down A means for all, UV, little E means in or is an element of. So this must be true for all U and V in the domain Rn. Again, for all U in the domain Rn. Okay. So we say that a linear transformation is some transformation T if addition is preserved and scalar multiplication is preserved. Okay. Okay. Every matrix transformation is a linear transformation. So every, let's see, all okay. That would be a great true or false question on like a test or something. Yeah. I'll write that there for those of you who are going to watch later. Okay. That does not mean that all linear transformations are matrix transformations. All matrix transformations are linear transformations. Okay. So now we're going to do a few proofs. Not rigorous proofs, but heavy in computation. So sharpen your pencils. So prove that the transformation T of U V is a linear transformation. Okay? In order to do this, we have to first define a U and a V, and then show that first addition is preserved, and second, that scalar multiplication is preserved. Okay. So so we have defined the two vectors. Let's see, the first condition we want to show is that T of U plus V equals T of U plus T of V. We're going to start with the left, show that they're right. Okay. We're just adding vectors here, right? We add the corresponding components. Now we use my transformation. U minus V gamma U plus 2V. Okay, clean things up a bit. Okay, so from here to here, I'm noticing that this is right. This is just the component addition of these two separate vectors, right? Here's U1, U2 plus V1, U1 minus U2 plus V1 minus V2, right? And then, oops, get that guy out of there. This guy plus that guy's here, okay? And this amounts to this up here. This is T of U plus T of V. This is T of U because I'm taking this transformation and applying it just to U. And this is T of V because I'm taking this transformation and applying it just to V. Started with the left, got the right, shown. We're going, for time's sake, we're going to skip showing the scalar multiplication, but that one's pretty easy. It's just a lot of distributive property over and over and over again. Okay. All right. There are a lot of really good examples in here that would have been much easier to do in class. We're going to skip some of these. And move on to 1.9. But all the examples that we're skipping are just like this one. It's prove this. Here's, how you would go about it. You're really just taking the left, showing that you can get the right. Okay. So 1.9 is much more involved, and I don't want to take up your entire day, whether it's your entire day right now or your entire Saturday or whatever you decide that you're going to watch this. All right. 1.9. The matrix. Okay, 1.9. So we want to be able to write formulas for geometric transformations, right? Be wonderful if we had an idea of some geometric transformation that we would like to do, and then we could come up with a formula like that. Okay. Every linear transformation from Rn to Rm is actually a matrix transformation, x to ax. Okay. The key to finding A, which boils down to the key to finding the function for mapping x to ax, is determined by is to observe that T is determined by what it does to the columns of the n by n identity matrix, I sub n. So we have a term, I sub n, the identity matrix, which is right. Could be as big or as small as it needs to be, but it is square, n by n. So this would be the I3 identity matrix. Every column has a label. These are E's. up to the ith e. So let's look at an example. Suppose T is a linear transformation from R2 to R3. Where this is the case. The transformation of the first column of the identity matrix maps to 2, -3, 4, and the second column of the identity matrix maps to 5, 0, 1. Okay, and I'm asked to find T of X for any X. In other words, what is the transformation? What is the matrix A? What matrix A will take any X in R2 to R3, with these being sort of conditions that we have to follow. So we know that any vector X in R2 can be written as write this down here. Okay, so any vector in R2 we can write this way, right? Because these were my columns of the identity matrix, right? This will give me X1, this will give me X2, okay? Then we could say that T of X is equal to this, which, since we know this is a linear transformation, addition must be preserved, is the same as x1 times t e1 plus x2 t e2. Well, we know how those behave, right? So this boils down to x1 times 2 negative 3, 4 plus x2 5, 0, 1 which is 2x1 plus 5x2 negative 3x1 plus 0 x2 4x1 plus 1 x2 thus A must be 2 negative 3 4 5 0 1. Okay. So that's great if we know what these are. If we know how the transformation acts on the columns of the identity matrix. It's very simple. Let's talk about this theorem. This is theorem 10 in your book. Such that So theorem 10. So say we know T is a linear transformation, then there must exist a unique matrix A such that we can model the transformation T as the multiplication of A times any vector X in the domain Rn. Okay. In fact, A is the m by n matrix whose jth column is the vector T of E sub j, where E sub j is the jth column of the identity matrix. Matrix A is called the standard matrix. Okay, the standard matrix for linear transformation T. Okay. Linear transformations focuses on particular properties of mappings, and a matrix transformation describes how such a mapping is implemented. Okay. So that's sort of the difference between linear and matrix transformations, right? Okay. Linear transformation has a particular property, and the matrix transformation describes how that transformation occurs. All right. Find the standard matrix. All right. Let's see. A few examples here. All right. So let's see. Okay. Standard matrix. Find the standard matrix. Oh, excuse me. So we want to find the standard matrix of the transformation from R2 to R2. That is a horizontal shear wrong shear Okay, so we want to find the standard matrix of the transformation T from R2 to R2. That is a horizontal shear, right? That's this sort of thing, okay? That leaves the first column unchanged and maps the second column to R2 plus 3 times the first column. All right, well, this could be written as this. Okay. E1 we know is 1, 0, and that needs to stay unchanged. And we're mapping E2 to this, which is 3, 1. Okay. So my horizontal shear, or in other words, matrix A, 1, 3, 0, 1. Right. So that leaves E1 unchanged. No, it doesn't. Well, let me double check what's going on here. because I get 3, 1 out of that. Oh, 0. And then if I did 0, 1, I would get 0, 1. So this should be no, this is right. I just think that the word horizontal is wrong. No, it is right. Horizontal. I'm going horizontal. Right. Okay. All right. Let's look at a different example and see if we can't. So find the standard matrix. Okay. Oops. Nope. Okay. So we want to find the standard matrix transformation that first reflects points through the horizontal x1 axis and then reflects over the line x2 equals x1. So thinking about this in the Cartesian plane, we want to flip over the x-axis and then reflect over y equals x. Okay, so we want E1 to go to be mapped. So let's see. E1 is not going to change initially. Okay. But then we want it to be turned into E2. So that's a total of 0 over 1, right? But that is right. E2, we want to initially be mapped to negative E2, right? That's the reflecting over the horizontal. Okay. And then we want to reflect it over the x. So we want to change it to E1, but it's got to be negative. Okay. So negative 1, 0. Okay. Putting these guys together, we have 0, 1, negative 1, 0. All right. That was a much cleaner way of doing that. Okay, and then had we been in class, I would have shown you some slides. These are all in your textbook, but there are lots of standard matrices that do a lot of these mappings. These are all in your textbook. These are actually cut and paste from your textbook. Here's our shear matrix. This is the first example we looked at. And then there's some matrix projections, right? If I wanted to project onto one of the axes, the x1 or the x2 axes. All right. Almost done. Oh, how long has this lecture been? It's been quite long. Okay. We need to talk about onto and one-to-one. So a mapping T from Rn to Rm is said to be onto if each B in Rm is the image of at least one X in Rm. So if each B in Rm is the image of at least one X in Rn. Okay. I.e. all of the codomain is used. Example. Right, is onto because everything in the possible range. This is a mapping from R1 to R1, but that's okay. It's onto because it takes everything, or at least one thing on the x-axis goes somewhere on the y-axis, right? Okay. And then let's see, what do I want to call it? So this, we have, in other words, an example and determined by a mapping is onto if columns of A span Rm. Okay. So if the columns of the transformation matrix span Rm, then that means everything in Rm is going to get hit. Okay, a mapping is said to be 1-to-1 if each B in Rm is the image of at most 1x in Rn. Okay. So 1-to-1 if each B in Rm is the image of at most 1x in Rm. So here on2 is sort of like a coverage. Are we covering all of the codomain? And here does only one domain value go to a specific codomain value? Okay. So, in other words, each B in Rm of the equation T of x equals B is, excuse me, solutions of the equation are unique or non-existent. Okay. So this just means that if I am going, if some x is if some pre-image is going to some image in B, it is the only image that is going, pre-image that is going to an image in the codomain. Okay, determined by let's see, 1-to-1 if columns are linearly independent. Okay, so on to, here's the key, here's what we need to know. On to the columns span Rm, okay, and 1-to-1 if the columns are linearly independent. Okay. All right. I think I'm going to call it a day because that's been a lot of information. We'll figure out what we need to do to get caught up. Probably should have taught on Wednesday, but that's my bad. So I'll check my email for questions about anything today. I will post this video up on the Blackboard site. It's going to take me a little while to upload, but it'll be there in a minute. Well, not in a minute. It'll be there today. So check it out. I'll send an email out to everybody saying that this is here, and we'll pick up from here next class. And I still would like to have the test on this chapter next week. Whether it's, well, it would have to be Thursday. And I think we can do that. Yeah, I think we need to have the test Thursday. So let's, like I said, let's call it a day because this is a lot. And we'll pick up on Tuesday.